Jai Shri Ram. My name is Nisha Jia, working as Assistant Professor in the Department of Electronics and Communication Engineering with CT Puttur. Today I will be explaining about analysis of input and output characteristic of BJT in common emitter configuration. So as we know, common emitter configuration is the most commonly used configuration in amplifier circuits. So this is a circuit diagram we can see here. Common emitter configuration means emitter terminal is made common for the input and the output side. So here you can see the terminals of BJT: base, emitter, collector. So emitter terminal we are making common for input side and the output side. So input we are providing to the base with respect to emitter, and output we are taking at collector terminal with respect to emitter. So emitter is made common. So this is called common emitter configuration. Today we are going to study the input characteristic and the output characteristic of the BJT. So here you can see for this particular experiment we require regulated DC power supply and then one resistor of 120 kilo ohm and VC107 transistor, NPN transistor, and we require 3 meters here, that is to measure IB, VBE, voltmeter, and then IC, ammeter at the output side. And what we are doing is this VCE, again here we require 1 meter, but there is a parallel connection to the DC regulated power supply, so we can take the same connection from these two terminals. So it is 1 meter is sufficient, so this we will be using, that is VCC. Okay. So you can see here the circuit diagram. So this is a regulated DC power supply and the 3 meters. This is VBE, IB, and then the IC. So here you can see the 120 kilo ohm resistor. So to which we are providing the supply, that is the supply plus positive terminal which is connected to the resistor, and the resistor other end should be connected to the meter. Okay, so that is IB positive and IB negative is going to the base terminal. So you can see here the transistor that is from the notch, it is facing upwards. This is emitter, base, collector. So we are providing your ammeter negative to the base. Okay, and then to the base again we are connecting the VBE parallel. So voltmeter positive should be connected to the base and voltmeter negative should be connected to the emitter, because emitter terminal is grounded. You can see here in the circuit diagram. This is what I have explained now. Resistor positive should be connected to the ammeter positive. Resistor other end should be connected to the ammeter positive. Ammeter negative should be connected to the base, and from the base again you have the positive terminal connection for the voltmeter, and negative should be connected to the emitter. This emitter terminal is common. So this is the common point, that is a ground point. And later the collector terminal, you see here collector terminal is connected to the emitter negative, and emitter positive should be connected to your regulated power supply, and regulated negative should be connected to the ground. So same thing we have made here. You can see the collector terminal. So this is the collector terminal. Collector terminal, ammeter negative. See, ammeter negative and ammeter positive should be connected to the power supply positive. So we have made this common. Okay. So this is the power supply positive and power supply negative should go to the ground. So this is connected to the ground terminal, that is emitter. So this is our common point. I hope the connection is understood. Let us see the operation now. That is, the first one is the input characteristic. So this is our VBB and this is our VCC. So let us switch on the power supply. So you have to keep both the inputs as 0, 0. Set the input voltages to 0, 0. So for the input characteristic, what is the procedure is, we are keeping the output voltage constant, that is VCE constant. In our case it is VCC only because we have made VCC and VCE common. So VCC is equal to some constant voltage. Set the constant voltage here, and we are going to vary the VBB. That is an input voltage, whatever we are providing. No? So we have to vary this input voltage VBB. So when you vary this, what happens? The amount of current flowing in the base terminal as well as the VBE, that is base to emitter voltages, it will get varied. So it is like common emitter configuration. We know BJT has 3 terminals, so it has got 2 junctions, base emitter junction and the collector base junction. This emitter base junction has to be forward biased, and the collector base junction has to be reverse biased. So it is just acting like a diode in these 2 junctions. So when your voltage, that is VBE, it gets 0.7, what happens? The current automatically drastically changes. IB drastically changes. So first you need to keep the input voltage 0 here. Set the output voltage some constant voltage. Let us set it to 1 volts. Set the input voltage to 1 volt. Yeah. So our output voltage is constant now, that is VC is equals to 1 volt. Now I am varying the VBB. So when you vary the VBB, you can note there is a changes in the VBE at IB. Okay, so when VBE reaches to 0.7, you can notice there is a drastic change in the amount of current flowing. So let us change the input now. So VBB, so you can see there is a changes in the VBE as well as IB. Now to keep VBE in 2 volts DC, and then here it is 200 micro IB in the range. So slowly increase the voltage. You can see that this VB is equals to 0.5 now, and current is equals to 4.3 micro. So when it reaches, VB reaches 0.7, it is like diode starts conducting. See now, it is 0.7. 0.69, you have 64.1. Once it crosses 0.7, there is a drastic change, 85.2 micro. You can see, still if you increase the voltage, yeah. So this is the drastic changes in the current. So when you plot the graph, IB versus VBE, so this is what we have seen. We are keeping VC is equals to 1 volt and slowly increasing the VBE. When you increase the VBE, when it reaches 0.7, after 0.7 it starts conducting, so there is a drastic change in the current IB. So this is what your input characteristic. And next, the output characteristic. So what is the procedure for output characteristic is, you need to keep the input current constant. So what is the input current here? IB is the input current. So IB, so let us make IB. See, this is our IB. We have to keep this constant. So let us take some 3 different values. IB is equal to 20 micro, 40 micro and 60 micro, and you are going to observe IC, and you are going to observe the IC and then VC. Okay, so here keep IB is equals to 20 micro. So change this until you get 20 micro. Yeah. Set this to 20 micro, and slowly you can change this VCC. VCC is nothing but your VCE. So in steps of some 0.5, we can take the readings. Yeah. So this is for 0.5. Yeah, you can note down the IC value. IC is 6.2 milli. So IC, you know the range, it is in milliamperes, IB in microamperes. So you have to keep it in the range of the IC should be 200 milliamperes. So for 0.5 VCE, you are getting 6.2 milli. So when you increase, you can increase in steps of 0.5. So this is for 1 volt. 1 volt it is 6.3. Yeah, so you are getting constant. So you have to start from 0.1, 0.2, like that you have to take. So it will increase first, and then after 0.5 onwards it will be constant value like 6.1 or 6.2. So now we can see after 0.5, yeah, you are getting some constant value. If you want accurate, then you can keep it in 20 milli. So it's not actually constant, little bit it will be increased. Yeah, you can see 6.4. See, so this is how we will be getting. Similarly, so this is for IB is equals to 20 micro. 20 micro. Similarly, you can take the readings for IB is equals to 40 micro as well as for 60 micro. So when you draw the graph, you will be getting the graph like this. So you are increasing the VCE and you are keeping IB constant. So we have kept IB is equals to 20 micro. Initially it was increasing, and after some voltage it will be constant. You will be getting a constant value, that is IC is equals to constant. So this is the region where your BJT is acting as an amplifier, that is an active region. Thank you.